Welcome to Nardar Academy. In this video, we are going to discuss about limit points. See, a point P in R is said to be a limit point of the set S if every neighborhood of P contains a point of S different from P. That means, that is P minus epsilon to P plus epsilon is a neighborhood for P, no? Right? By varying this epsilon, you will get different neighborhoods for P. So, whatever neighborhood you take, that point will contain a point of S other than P. Okay, so different from P, the neighborhood contains a point of S. So that type of point is called what? Limit point. The collection of all limit points of a set is called its derived set, and it is denoted by S dash. So let's see some examples. So the first one is every real number is a limit point of the set of rational numbers Q. Okay, see, that is, if P is a real number, then what is the neighborhood of P? P minus, see, this is the real line and this is a point P, and I am taking P minus epsilon to P plus epsilon is a neighborhood. In real numbers, you already know in the real line, whatever open interval you take, okay, that open interval will definitely contain infinitely many rational numbers, isn't it? So that is true for this open interval also. So this neighborhood P minus epsilon to P plus epsilon will contain infinitely many rational numbers. Therefore, this P is a limit point for Q. Okay, since this P is an arbitrary real number, this is true for any real number. Therefore, what we conclude, every real number is a limit point of the rational numbers Q. So, therefore, the derived set Q dash is equal to R. Next one is, we are going to see what is the derived set of any open interval in R. Alright. So, see here I am taking this open interval 0 to 1. I am going to find out the limit points for this open interval 0 to 1. See, this is the open interval 0 to 1. So, for proving any problem, that is for finding limit points for any set, first you consider the points of the set itself. Okay, then you go beyond the set. First, let me take any point here inside this open interval 0 to 1. See, if I take a point here, no, then definitely whatever your neighborhood for this point you take, it will contain a point of this open interval other than the point itself. So, whatever point lying inside this open interval will become a limit point for the set. Okay, right? Can you understand? So, whatever point you take, even if you take a point here, every neighborhood of the point contains a point of the set. Therefore, every point inside the open interval will become a limit point for the set. Okay, so inside points are all limit points. Therefore, every point of 0 to 1 is an interior point of itself. Next one, let us consider the boundary points. In the boundary, you have 2 points now. One is 0, another one is 1. They are not included. Actually, they are not included in the open interval. But still, if you take any neighborhood for 0, it will be like 0 minus epsilon to 0 plus epsilon. This right hand side part of the open interval will lie within our set, no? Therefore, every neighborhood of 0 will also contain the point of the set. And similarly, the same justification for 1 also. 1 is not a point on the set. But still, every neighborhood of 1 minus epsilon to 1 plus epsilon, the left hand side of this open interval will lie inside the set, no? Therefore, what do you conclude? Every neighborhood of 0 will contain a point of open interval 0 to 1, and every neighborhood of 1 also contain the points of the set 0 to 1. Therefore, 0 and 1, they are also limit points for the set yes. So, what do we conclude? Both 0 and 1 and all the points within 0, 1 are all limit points for the set. Next one, you go out of the set. That is, apart from the 0 and 1. If you go left side to 0 and if you go right side to 1, any other point cannot be a limit point, because whatever point you take, that will definitely not contain points of the set, no? Therefore, other points cannot be limit points for the set. So, finally, what do we conclude? The limit points of the set open interval 0 to 1 are 0, 1 and all the points of the set. So, together how do we write? The derived set of 0 to 1 is equal to closed interval 0, 1. Okay. So, in the set of real numbers, whatever open interval is given to you, the derived set of the open interval is equal to the closed set. Right? Okay. Then next example is Z, the set of all integers. This has no limit point in R. That is, any real number cannot be a limit point for this set. Actually, this set has no limit point. Okay. So, Z, that is the set of all integers, no? 0 plus or minus 1 plus or minus 2, etc. So, for every problem, first you consider the points of the same set itself. So, let P be a integer. Then whatever may be the integer, if you set epsilon is equal to half, then p minus half to p plus half will be a neighborhood, no? That is, for example, if you take p equal to 1, if you take special case I am writing, if you take p equal to 1, then you consider the neighborhood 1 minus half to 1 plus half. Okay, this is also a neighborhood for p, no? That is for epsilon equal to half. So this is equal to what? 1 minus half is what? 1 by 2 comma 3 by 2. That is this interval 1 by 2 to 3 by 2. If you plot the interval, this is 0 and this will be what? Your 1 by 2 and this will be your 1 and this will 3 by 2 means what? 1.5, no? So this will be your 1.5. Right? So this is the interval which contains the point, but this contains only the point, exactly it contains the point 1 only, no other points are not there. So for integers it will contain 0, 1, 2, 3 etc. But if you consider this neighborhood 1 by 2 to 3 by 2, it will contain only one point, that is one of the integers, other points are not there. But what is the definition for limit point? Every neighborhood must contain the point of the set other than p. Okay, so other than 1 it should contain some other point, but here it is not true. Therefore p is not a limit point, that is 1 is not a limit point. So this is true for every integer. Therefore any integer, that is all the points of the set, are not limit points for z. So the points of the same set itself, they are not limit points. Okay, so that we have concluded. Next one, consider any point which is not an integer. Okay, so now which is not an integer I am taking, then so p is a real number but not an integer, no? But what can we do? So even if it is not an integer, I can find an integer j which is less than p and j plus 1 which is greater than p. Then this open interval j to j plus 1 will contain only one point p, isn't it? And even that point will also not contain any other integers, because j and j plus 1 are two consecutive integers, no? I will explain with an example. Suppose if you take p equal to 0.5. Okay, if you take p equal to 0.5, what I am saying is the 0.5 is there, no? You consider the integers, nearest possible integers. What are the nearest possible integers here? This is what, greater than 0, isn't it? 0.5 is greater than 0 and less than 1. So then 0 to 1 is a neighborhood for this point p, which does not contain any point of z, isn't it? Intersection with z is equal to what? Empty set. Okay, so whatever real number you take, you can find a neighborhood which does not contain any point of z. Therefore this point p is not a limit point for z. So this is true for any non-integer real number. Therefore what do we conclude? Z has no limit point in R, or otherwise the derived set Z dash is equal to phi empty set. See, for proving something is not a limit point, you have to find at least one neighborhood which does not contain any other point of S. Okay, so here I have find out one neighborhood which does not contain a point of Z. This is enough. For proving it is a limit point, you have to prove every neighborhood contains. For proving it is not a limit point, you have to find only one is enough. This neighborhood is not containing means it is not a limit point. Okay, right. Next one is a finite set in R has no limit point. So previously we have proved it for Z. Now we are going to prove whatever finite set you take in the set of real numbers, that will not have any limit point in R. So for that I am taking S equal to A1, A2, etc. A and be a finite set in R. So I have to prove this set does not have any limit point. See, if these will be arranged in some order, no? Because R is an ordered set, so we can arrange the elements of S in some order. Suppose if you take any number beyond this set, that is less than A1, right? See, let me mark the points here. So this is my real numbers. Let me take points A1, A2, A3, etc. up to AN here. So this is my set. If you take any points on this side, this will be from minus infinity to A1, no? If you take any point S here, I cannot find any limit point, because whatever point you take, its neighborhood will definitely not contain any points of the set S. Therefore, points below this A1 cannot be a limit point. And similar case for points above AN, that is P greater than AN cannot be limit point. Next one, let P equal to A1. This corner point is there, no? P equal to A1. Then I can find a neighborhood here. See, I can find a neighborhood in this interval which contains only the point A1, not any other point of S. Therefore, this is not also a limit point. P equal to A1 is not a limit point. Next one is, suppose in between point AK also if you take, suppose P equal to AK, even if this point you take, then I can find a neighborhood ak minus 1 to ak plus 1 which does not contain any other point of S other than ak. Therefore, that is also not a limit point. So what are the things we have proved? Points below a1 and above an, and points, corner points a1 and ak are also not limit points, and point ak in between, it is also not limit point. So all the cases we have proved. So finally what do we conclude? So what do we conclude? This has no limit point. Okay. Next one, the set S equal to collection of all 1 by n where n is a positive integer has 0 as the only limit point. Okay, first I will tell you how to find the limit point directly, then I will go to the theoretical proof. See, 1 by n means they are all decimal points only that will lie between 0 to 1. See, this is 0, this is 1. For n equal to 1, it is 1. For n equal to 2, it is 1 by 2, 1 by 3, 1 by 4, 1 by 5, etc. So all the points will be very close to 0 only. So all the points below 0 and above 1 cannot be limit points. 1 can also is not a limit point because only one point is there, so it is not a limit point. 1 by 2 is also not a limit point. 1 by 3, 1 by 4, they are all not limit points. Only 0 is the limit point because as n tends to infinity, this series goes to 0 only, no? Therefore, around 0 only you will be having infinite numbers of the set. Therefore, 0 is the only limit point. Let's see theoretically how to prove. Suppose p equal to 0, okay, then by Archimedean property, for any epsilon greater than 0, there exists a positive integer m greater than 1 by epsilon. That means 1 by m is less than epsilon. So that means 1 by m belong to the interval minus epsilon to plus epsilon. That is 1 by m belong to S intersection, because S is what? Set of all numbers of the form 1 by n only, no? S intersection minus epsilon to plus epsilon. Therefore, every neighborhood minus epsilon to plus epsilon is a neighborhood for 0, no? So every neighborhood of 0 contains a point of S, 1 by m. Okay, therefore p equal to 0 is a limit point. So it is a 0, 0 is a limit point we have proved. We have to prove next any other point is not a limit point. So now we consider the case that is minus infinity to 0. Definitely it cannot be a limit point because our set contains only positive numbers. And similarly 1 to infinity cannot contain any limit point because our set contains all the points which are between 0 and 1. And now you consider 0 to 1, the points between 0 to 1 which is not in the form 1 by m. Then in that case p doesn't belong to the set S. See, consider I have plotted here. This is 1 by 2 and 1 by 3. In between I have taken one number which is not in the form 1 by m. Then you choose a number m such that 1 by p lies between m to m plus 1. In that case, p lies between 1 by m plus 1 to 1 by m. The similar case here, see, this is p. Then this p lies between 1 by 3 to 1 by 2, no? Then this is 1 by 3 to 1 by 2 is a neighborhood which does not contain any other point of S other than this point, isn't it? Therefore, this is not a limit point. Okay, and for p equal to 1 also it is not a limit point because half to infinity is a neighborhood. Already I have explained you in this diagram itself, no? 1 is not a limit point because a small neighborhood here you have to take that will contain only one. Other points of S are not here. Okay, therefore p equal to 1 is also not a limit point. Next one, let p is not equal to 1 and p be a point of S. This is ulta for this case, okay, that is p equal to 1 by m. In that case also, see, you can choose two numbers, 1 by m plus 1 to 1 by m minus 1 is a neighborhood which does not contain any other point of S. Therefore, what do we conclude? 0 is the only limit point for this set. Then the next problem, see, let's see some examples. 0 to infinity, open interval 0 to infinity. I already have told you, whenever you get an open interval in the set of real numbers, just you put its derived set is equal to the closed interval. So the derived set for open interval 0 to infinity is half open interval 0 to infinity. Whenever you have infinity, you have to put open interval only there. So this is closed at 0, infinity. That is all the numbers starting from 0 are limit points. Similarly, the derived set, this is derived set for minus infinity to 0 is equal to minus infinity to 0 are closed. Next, limit points of 1 plus 1 plus 1 by 3 power n belongs to Z plus. How to find the limit points for this? See, if you plot the points for this, it will be like, see, this is 1 and this is 2. All the points will be between 1 and 2. So, the first point will be equal to what? 1.33. The second point will be 1.11. All the points will be very closer to 1 only. So, p equal to 1 is the only limit point. So, derived set is equal to 1. Next one, r minus set of all 1 by n belongs to Z plus. That is, in the real number set, we are removing only the points of the form 1 by n. Even for this also, every neighborhood, sorry, every real number is a limit point for this set. Next example is 1 by m plus 1 by m 1 by n, where m and n are positive integers. See, for this one, just you write, you fix n, vary m, then what will you get? 1 plus 1 by n, 1 by 2 plus 1 by n, 1 by 3 plus 1 by n, 1 by 4 plus 1 by n, etc. So all these, here you can vary n, so that you will get one sequence here, one sequence here, right? So here all the points will be very closer to 1. Here all the points will be very closer to 1 by 2. For this sequence it will be very closer to 1 by 3. For this sequence it will be very closer to 1 by 4, etc. If you go on up to infinity, it will be very closer to 0. So the limit points are 0, 1 by 2, 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, etc. So the derived set is 0 union 1 by n, where n belong to z plus. Okay, that's all. Thank you.